Hello, everyone. My name is Janmesh, Kalra, and I will be presenting the paper titled Predicting Atmospheric Air Pollution, a Convolutional Transformer Approach for Spatial and Temporal Analysis of PM2.5 for ICDATA 2023. Air pollution as a global threat. As countries across the world continue to urbanize and move towards more industrial practices, congregation in the central business districts continue to contribute high levels of air pollution, particularly PM2.5. PM2.5, also known as particulate matter PM2.5, is pieces of matter that are in the atmosphere caused by different forms of pollution that are occurring, such as household cooking, fuel, motor vehicles, natural fires, and amongst many other different types of causes. In the last decade, deaths caused by PM2.5 increased by 23%. The problem of air pollution is only growing as time progresses. And PM2.5 has direct correlation with diseases such as COPD, asthma, pulmonary fibrosis, and pneumonia. Different types of research show that PM2.5 can lead to premature deaths. It can aggravate current health conditions of people, and it is a concern that governments have taken into their own hands and have decided to act upon it. 6.7 premature deaths occur annually due to this household ambient air pollution. And we can attribute that towards PM2.5. PM2.5 has the ability to travel deep into human respiratory tracts and cause these premature deaths. Now, through our research, we're trying to examine PM2.5 at the hourly level. We're trying to figure out where PM2.5 is occurring at the source and how we can predict its future patterns and form a solution to the situation before it aggravates even further. So our model follows a spatial-temporal model. In this, we trace how PM2.5 changes over time for the temporal portion. And for the spatial portion, we studied the way PM2.5 disperses over a geographic region. So let's say if we're studying LA County, we would examine how PM2.5 changed from 2018 to 2020. That's our little temporal range. We want to examine how the levels change over time. But we also want to see which parts of LA County is PM2.5 dispersing further on, and where are the problem points at. So our model sets apart from other research in the field because it combines these two sort of channels together. It makes a spatial-temporal approach. In order to accomplish this, we join two machine learning techniques. We have the convolutional neural network, which has image-like inputs to understand the spatial patterns in our data. This takes in remote sensing data from satellites, and it tells us where on the grid the PM2.5 patterns are occurring. And based on that, we apply image convolution to predict how it'll occur in the future. For the temporal portion, we use a transformer approach. We try to figure out how these inputs spread across the time period and how we can relate this to our spatial patterns. Now, when we combine both of them together, we get our convolutional transformer architecture. In our previous edition of papers, we wrote about a convolutional LSTM structure. This LSTM structure combined the same sort of spatial temporal approach, but it used an LSTM instead of a transformer. But we have found that the transformer is a lot more retentive and is better at retaining information for our purposes. It follows a similar pattern of a similar architecture to our convolutional LSTM model in that it has a sequential encoder and decoder, which understands the relationship between the target and input frames. A little bit more about the transformer. So our transformer relies on a mechanism known as multi-head self-attention. These multi-head self-attention layers are built into our convolutional transformer architecture. And what they do is that they allow for parallel operations. Before, the LSTM would go one by one into each frame, trying to understand the data, and then performing an operation on it. Now with the transformer, we're able to make the process in parallel and reduce the computational expense. We're also able to retain more information per kernel in this approach. A little bit more about how this multi-head self-attention portion of the transformer works is that it takes our input sequence and it multiplies it with this learned weighted matrice. And from that formula, it obtains a key, query, key, and value vector. Then we can utilize these query, key, and value vectors to assign attention scores. Attention scores are mathematically calculated with the formula presented on the screen. And once we get all the attention scores for each frame, we can combine them into a weighted sum in order to generate an output, which is what our prediction would be. So with this project, one of our main goals was to predict PM2.5 at the hourly level for LA County. At a higher level, what we are doing is we're trying to figure out how the past 24 hours can affect the future 24 hours of a certain region. We utilize remote sensing inputs, meteorological-based data, and ground-based PM2.5 data. In this case, the ground-based PM2.5 data is our ground truth label. And from that, we form spatial temporal predictions. And this is an example of our model when it ran with all the inputs that'll be further described in the next slide. Data collection. As a reminder, the temporal bounds of our research spanned from January 1st, 2018, all the way to December 31st, 2020. In this time span of 3 years, that amounts to 26,304 hours. And since we're trying to predict PM2.5 at the hourly level, we would have to collect all our data at the hourly level from the various sources that we used. For our model, we use remote sensing inputs as well as ground-based meteorological data. For remote sensing, we had various different types of instruments. One of the first being the NASA MERA-2 satellite, which had gridded fire features. These features included surface air temperature, surface exchange coefficient, and planetary boundary layer height. As shown in figure E to the right, that is the MERA-2 satellite gridded onto our model input. MERA-2 has a bunch of different bands that are very useful for our analysis. PBL height allows us to quantify the distance between the ground level and the atmosphere, and it is highly impacted by weather conditions. Amongst others, surface air temperature, it would definitely have a direct correlation with PM2.5. If the air temperature is higher, it is likely that there's going to be more pollution occurring in the area. We also utilize the NASA MODIS MIAC algorithm for AOD. AOD is a comprehensive measurement of many different pollutants in the atmosphere, such as NO2, carbon monoxide, and methane, and it gives us a very comprehensive view of all these air pollutants. It is considered to be one of the most important inputs into our model, and it is shown to the figure on the right as box F. We also use the ESA Sentinel-5 tropomy instrument, as shown in part B of the figure on the right. This satellite directly measures some of the pollutants we want to study, So CH4 methane, also NO2, nitrogen dioxide, and carbon monoxide as well. So these all these inputs combined together make up the remote sensing portion of our model. Furthermore, we also use ground-based meteorological data, and for that we sourced GridMet. So GridMet provides an hourly static frame of how, a yearly static frame of the averages that occurred throughout the year. So for 2018, there was one frame, 2019, there's a frame, and 2020, there's a frame. And it gives us the following bands that we used: wind direction, wind speed, and precipitation. So precipitation, that's rainfall. So we would figure that if there is higher rainfall, there is a chance that climate change is changing, and there is certain meteorological factors that could be increasing the level of PM2.5. Wind speed, that directly tells us how PM2.5 is going to be dispersing throughout the region, and wind direction goes along with wind speed. It adds on to the spatial part of our analysis. So we converted all of these inputs into geotiffs into the boundary of LA County, which is denoted with the following coordinates: 33.5 degrees north to 34.5 degrees north, and then 117.5 degrees west to 118.75 degrees west. And we, once we made this bounding region, we found out the data, the ground-based PM2.5 data from EPA Air Now, in order to use this as a label. Since we are predicting PM2.5 in the region, we wanted something to compare it with, so we used the EPA Air Now sensors as a way to compare our results with. So they serve as the ground truth label in our model. A little bit more about data pre-processing. So once we cropped and resized all the input sources, we had to fit them into 40 by 40 grids. And then we formed our predictions at the hourly level. So in order to do that, we used 24 hours of data in the past in order to predict the next 24 hours of data in the future. And we had to create these sort of bundles of 24 frames for each day, for a total of 1,096 bundles. And since each bundle has 24 frames, that would be 26,304 samples in total. So this gives us our 5D tensor size of 26,304 by 24 by 40 by 40 and 10. So that shape will be explained a bit further in the next slide. But the key takeaway here is that we are predicting data in the future using these bundles. So we first collect hours 1 through 24 for a day, and then we sort of have this sliding window staggered frame setup, where that if we have 1 through 24 in one frame, one bundle, then the next bundle will have 2 to 25, and then it'll move forward that way so that no overlap is missed. A little bit more about our convolutional transformer architecture. So we have this 5D tensor input. The shape, as explained in the previous slide, will be the samples followed by frames, rows, columns, and filters. So samples 26,304. Frames, we had the 24, because we have 24 frames in each bundle. And then we have 40 by 40 for the rows and columns. And then we have 10 filters in our model, which are each represented by the different inputs we have. So based on the inputs, we calculated the amount of filters we needed, and we got the value of 10 for that. So to form our model, we have 4 different channels. So we have 2 convolutional transformer layers, and then we have 2 convolutional 3D layers. So we chose the dimensions of 15 and 30 in order to make it more computationally efficient. We tried using different values of dimensions for this transformer model, but we found that 15 and 30 is best suited for prediction purposes. and the number of heads as follows was suited correctly. We also use the reload activation function as part of our convolutional 3D model in order to figure out how the relationship between the data is working. So between each input frame, if there's a positive correlation, then the value of reload would be positive. Whereas if there's no direct correlation, it would just be 0. In order to evaluate our model, we used several key different error metrics. We used NRMSE, which is normalized root mean squared error, and SSIM. NRMSE was not as useful in our analysis, so I'll be really just, I'll cover that later on, but the main focus of our error analysis was SSIM, which was structural similarity index measurement. So SSIM helps quantify the general similarities between a ground truth frame and a prediction frame, rather than the pixel by pixel. So it takes a more human-like approach where it tells us the broader structure, and it's a scale from 0 to 1. And we can tell how similar two frames are with this metric. So these are some of our model predictions that came after we ran the convolutional transformer. So as you can see, to the right, we have the ground-based PM2.5 EPA air now sensors. And then to the left, we have our predictions. So we have an SSIM of 0.85 in the first frame, 0.92 in the second frame, 0.91. So these are rather high values, indicating that there is a stronger similarity between these two. And we compared our model prediction results with some of our past papers that were submitted to ICDATA. So our convolutional transformer model initially performed a bit worse than our CSCI 20 paper, but then we found that after the first frame, it really begins to pick up and move at a much more efficient pace, outperforming both of our other past research papers. So we found that in this case, it takes a bit more initial learning cost, but once it is able to learn the input features better, it performs at a much better level than the other convolutional LSTM model. This is some more data to back up the conclusions that we supported in the previous slide. So we can see that these are the raw numbers where the first frame, we have the convolutional transformer performing a bit higher than the ICDATA 20 paper, but a bit worse than the CSCI 20 paper. And then we can see that from there on, the convolutional transformer outperforms all different other versions of the model. So in conclusion, throughout this project, we were able to source meteorological data, remote sensing inputs, and ground-based PM2.5 in order to incorporate it in the convolutional transformer model. We were able to develop a convolutional transformer model from scratch in order to predict PM2.5 at the hourly level for the defined region of LA County. We were able to compare these convolutional transformer results with our previous edition of models, and we were able to find that our convolutional transformer model outperforms our works on convolutional LSTM and our convolutional LSTM with graph convolutional network embeddings. A little bit more about this comparison, we found that 71.6%, there was a 71.6% decrease in the 5-frame average SSIM error compared to the convolutional LSTM model. And there was a 38.8% decrease compared to the meteorological GCN convolutional LSTM model. In terms of our future outlook with this research, we want to expand the amount of ground level PM2.5 monitoring stations in LA County. For now, we're using EPA Air Now as our ground-based label, but we want to incorporate more sensor locations in order to get a more accurate reading for the entire defined region of LA County. We also want to scale our model results to a higher resolution from 40 by 40 to potentially 200 by 200 in order to get a better depiction of where the air pollution is occurring in certain regions. We also want to study the broader implications of PM2.5 on respiratory diseases and understand how higher levels of ambient air pollution can affect it. We want to understand how PM2.5 can affect diseases such as COPD, asthma, and how it affects residents at a higher level, and what our research can do to help mitigate the effects of air pollution. Thank you for listening, and that was our presentation for ICDATA 2023.